One of the simplest questions we might ask in astronomy is how common are planetary systems like our own? Is the solar system, with its 8 coplanar circularly orbiting planets, a typical, even convergent outcome of planet formation? Or could it be that there's something special about our home, that most systems look nothing like our own? Attempts to answer questions like this often invoke the principle of mediocrity, which tells us that we should expect to be a typical sample. That principle is often characterized as a statement of cosmic humility, astronomical modesty. Isn't it audacious and egocentric to assume that there's something special about us? Yet, we have to also admit that rare conditions may be a prerequisite for the emergence of self-aware sentient beings such as ourselves. After all, in the solar system, none of the other planets have vegetation or biospheres or civilizations. At least in the context of the planets which orbit the Sun, the Earth is already unusual. The proponents of mediocrity might brush that away as a simple consequence of the fact that only the Earth is at the right orbital distance for surface liquid water. But that statement, in fact, precisely exemplifies the fallacy of blindly adopting mediocrity. Look, as a basic tenet, it's fine to assume that similar conditions lead to similar outcomes, but when it comes to life, we don't know what those necessary conditions are or how common they are in the universe. Perhaps the conditions necessary for life aren't limited to just being at the right orbital distance for liquid water. Perhaps they also include an inordinate list of extra criteria that are themselves so rare, especially to conspire at once, that whilst they might inevitably culminate in life, the fraction of stars with living worlds remains astronomically small. And so, when it comes to the question posed in this video, the mediocrity principle cannot be trusted, and indeed it will be shown later to be categorically wrong. Indeed, as a rule of thumb, it is precarious to invoke that principle whenever our existence is conditional upon the subject matter in question, which constitutes a strong selection bias. Far better to forget about mediocrity, cosmic humility, or claims of modesty, and just to focus on the data, openly and objectively. Fortunately, over the last 2 decades, astronomers such as myself have been vigorously hunting planets around other stars, so-called exoplanets. We now know of over 4,000 confirmed examples and 6,000 further candidates. And so, when we look at this catalogue of thousands of systems and ask how common are systems like our own, we have to first define what it is that we really mean by that question. After all, it's open to several interpretations. How similar does it need to be? Let's start broad and gradually narrow in on this question. And in particular, let's start with something simple. How common are planetary systems? What fraction of stars have some kind of planets around them? In 2009, NASA launched the Kepler Space Telescope, which was designed to count planets. Its primary mission was to reveal how often do stars like our Sun have planets like our Earth. Kepler did this by leveraging the powerful transit method, photographing about 200,000 stars simultaneously once every 30 minutes, in order to see if any temporarily dropped in brightness, betraying the presence of a planet transiting across the star and blocking out starlight. After 4.5 years of patiently staring at the same patch in the sky, the current Kepler catalogue lists 4,716 candidate planetary signals amongst those 200,000 stars. However, in many cases, Kepler detects multiple planets around a single star, so-called multi-planet systems, just like our own. So, accounting for this, we can add up that there are 3,567 Kepler stars with some kind of planetary system around them. Now, if Kepler were a perfect telescope, we could simply take that number, 3,567, and divide it by the total number of stars observed, which is about 200,000, to arrive at an occurrence rate of planetary systems, which would be here just 1.8%. However, For all of its glory, unfortunately, Kepler is not a perfect telescope. In fact, far from it. In fact, even the method that Kepler uses is fundamentally flawed. It can only see planets if they pass in front of their star, a geometrical requirement that demands that their orbital plane is nearly aligned to our line of sight. And so, of course, this represents just a tiny slither of the total planet population. For example, only about 1 in 200 of the stars around us have the right alignment to see the Earth transit in front of the Sun. But this is just geometry, and so it is possible to correct for this effect. In doing so, a recent Penn State study led by Matthias He estimated that the fraction of Sun-like stars with planetary systems around them is 57%, plus or minus about 10%. Of course, it is worth highlighting that only about 10% of stars in the universe are G-type Sun-like stars in the first place. If you want to learn more about that, you can check out our earlier video on the subject. On top of Kepler using a flawed technique, it is also an imperfect telescope. For example, planets smaller than the Earth are largely invisible to Kepler as a result of the limited physical size of the telescope at 95 centimeters. Yet more, planets orbiting their star on periods greater than about a year or so are generally missed by Kepler. That's because Kepler only looked at its patch of the sky for 4 years, and it needs 3 transits to make a solid planet detection. So that 57% number that I told you is surely a lower limit. Indeed, we actually see some support for that by comparing Kepler to other planet hunting techniques. Gravitational microlensing is sensitive to the much longer period cold planets that Kepler often misses. Indeed, recent work coming out of the University of Warsaw, led by Pilecki and colleagues, estimates that each microlens star studied hosts on average about 1.4 of these cold planets. Put together, whilst it might be an exaggeration to claim that all stars form planets, these analyses suggest that planets are the rule rather than the exception. Let's now dig deeper and ask what these systems typically look like. Astronomers often visualize the exoplanet population with maps like this. On the x-axis, we're plotting the orbital period, and on the y-axis, the planetary size. Each box counts up the total number of planets detected and then corrects for the various biases in play to estimate the underlying occurrence rate, here presented in percentages. A startling consequence of these maps is that the most common type of planet in the cosmos appears to be one with a size in between that of the Earth and Neptune. In fact, the majority of planetary systems around Sun-like stars appear to have one of these. There is, of course, no planet like this in the solar system, and so astronomers have been forced to describe them by analogy. One can either think of them as scaled-up versions of the Earth, so-called super-Earths, or scaled-down versions of Neptune, so-called sub-Neptunes. Their nature remains elusive and enigmatic, but their prevalence is clear. Learning about these worlds has been and continues to be a major goal of modern astronomy, and it will surely be a major theme of NASA's upcoming JWST space mission. Yet already, we can say that they often appear in multiple planet systems, but rarely reside at extremely close separations to their star. In fact, there appears to be an apparent desert of small Neptune-sized planets in ultra-compact orbits, despite the fact that we see rocky and Jupiter-sized planets in those kinds of orbits all the time. Perhaps this indicates then that these mysterious worlds ultimately get evaporated away into rocky cores under the intense irradiation of their star. Whatever the case, the fact that our solar system lacks one of these sub-Neptune planets is immediately odd. It already delineates our solar system from the ensemble out there. In fact, all of this talk of close-in planets brings about another striking observation. Many of these alien planetary systems we're discovering feature planets far closer to their star than we have. For example, adding up all of the boxes interior to Mercury's orbit using a similar published map by Foreman Mackey and colleagues reveals about 0.62 close-in planets per star. So again, this seemingly suggests something odd about our home system. Of these, it's worth pointing out that there is a subset of very close-in planets, such as the famous hot Jupiters. Hot Jupiters dominated exoplanet discoveries years ago because they're far easier to find, and I think it created the impression that they must be common. In fact, hot Jupiters are rare, with recent studies showing that less than 1% of stars have them. So, the fact that the solar system doesn't have one of these hot Jupiters, that is not unusual. In fact, it would be very bad news for us if it did, because such planets rarely have any neighbors, likely gravitationally casting smaller planets aside as they bulldoze their way through a solar system to the inner core. Hot Jupiters are fascinating astronomical phenomena, but ultimately objects which are not crucial to the question posed in this video then. But learning about the field more broadly is endlessly intriguing, and so when you're done watching our Cool Worlds content, a great place to find more documentaries about exoplanets, astronomy, and science more broadly is the sponsor of today's video, that is CuriosityStream. CuriosityStream is a subscription-based streaming service including thousands of shows spanning science, nature, technology, and history. You can think of it as the Netflix for nerds or the Hulu for history buffs, featuring award-winning exclusives and originals available on everything from your smart TV to your smartphone. For example, I've enjoyed watching the Living Universe show, which goes from exoplanet discoveries to imagining the kinds of life that might inhabit the cosmos. I have to also give a shout out to Ancient Earth, which my kids and I have been binging on, filled with dinosaurs and prehistoric vistas. You can sign up and start watching today using the link curiositystream.com/coolworlds, which will give you a full year for just $14.99, which is frankly a bargain. So check them out using the link down below in the description, and thank you once again to CuriosityStream for sponsoring us today. Coming back to our solar system, at this point, we can say that it lacks two rather common properties. First, it has no planets interior to 1/3 of an AU, and second, it has no mini-Neptunes. Perhaps Planet 9 is our missing mini-Neptune, but even then it wouldn't really help as it's extremely distant and not representative of the types of planets that Kepler is detecting. All of these discussions of unusualness, though, are frustrated by the fact that analogues to most of the planets in our solar system are invisible to a telescope like Kepler. As already discussed, planets beyond the orbit of Mars have too long a period for Kepler to detect, but what about the inner planets? Mercury is certainly too small, but even Venus and Earth are just below the sensitivity level. It's actually startling that Kepler failed to detect any true Earth analogues. All of our estimates of the occurrence rate of Earth-like planets are essentially extrapolations of the other trends into that region. If you want to learn more about this, then you can check out our previous video on the subject. Kepler isn't the only game in town though. Radio velocity surveys have impressive sensitivities too. This is where astronomers look at the wobbles of stars to infer the gravitational influence of companion planets. For this method though, previous surveys are just simply not sensitive to Earth-like planets around Sun-like stars. However, unlike Kepler, these radio velocity surveys have been monitoring the sky for decades, not just years. That means that they are sensitive to something like Jupiter with its 11-year period around the Sun. Perhaps focusing on alien Jupiters then provides the key to finally understanding our uniqueness. Boiling the entire solar system down to just one planet, Jupiter, might seem a little useless, but remember Jupiter is no ordinary planet. It dominates the planetary mass budget, the angular momentum of the solar system, and shepherds around the other planets. To put it bluntly, Jupiter rules the solar system. So here we actually have a method that is sensitive enough to detect analogues to the solar system. In a 2016 study, Wittenmeyer and colleagues report that 6.2% of Sun-like stars have a Jupiter analog, and other studies too generally converge on a number of about 10%, depending on how one defines a Jupiter analog. Now, crucially, amongst this 10%, of course, the rest of the system isn't necessarily a solar system analog, even if that Jupiter is. But if we are willing to define a key feature of our solar system to be that it has a Jupiter-like planet, then the fraction of stars with solar system-like systems cannot exceed 10%. To say that clearly, just one more time then, that means that less than 10% of Sun-like stars have solar system-like architectures. That's the kind of definitive empirical statement that we love here on Cool Worlds, and as hinted at earlier, it clearly undermines the mediocrity principle, which would have erroneously predicted solar systems to be the norm. In 2018, a Caltech team led by Marta Bryan found that if a system has a known super-Earth or sub-Neptune around it, the chances of it having an outer Jupiter are greatly enhanced. Specifically, they find that for systems with a known 1 to 4 Earth radius planet, they have a 40% chance of having an outer Jupiter, so that's 4 times higher than the average. It's tempting to flip that probability around somewhat naively and say that therefore any system with a Jupiter has a 40% chance of also having a super-Earth. If that were true, then the fact that the solar system, which has a Jupiter, that doesn't have a super-Earth, that is neither an unusual nor typical outcome. But the act of flipping odds around like this requires the use of Bayes' theorem to do properly. Writing out, we can say that the probability of a system having a super-Earth, given that it has a Jupiter, equals the probability of having a Jupiter, given it has a super-Earth, that's Bryan's 40% number, multiplied by the probability of the system having a generic super-Earth, which from Kepler is about 30%, and then finally divided by the probability of having a Jupiter analog, which is the 10% number from before. Putting in the numbers, this gives a probability of 120%, which at first doesn't seem to make sense. I mean, how can it be larger than 100%? The answer is that those numbers all have big uncertainties on them, and when you actually correctly propagate those errors through, you get a giant error bar of about plus or minus 50%. So don't worry, we haven't broken statistics here. There is still plenty of space for reasonable solutions. But the real point of this calculation is that it suggests that the vast majority of these Jupiter-like planets indeed go on to have super-Earths in their systems. We might guess something like at least roughly 3/4 of them. So in that context, the solar system is weird in not having a super-Earth, especially when we factor in the fact that we have a Jupiter. Now, is there anything else that we can possibly say about this population of detected Jupiter analogs, really the closest thing we have to solar system analogs, in order to understand our own uniqueness? One other key property that radial velocities measure is the orbital eccentricity of an exoplanet. In other words, how elliptical is the shape of their orbital path. In the solar system, the planets follow almost circular orbits, which corresponds to an eccentricity value of 0. An eccentricity greater than 1 would correspond to a parabolic trajectory, something like Oumuamua, which can't sustain a stable orbit at all. Looking at Jupiter, it's pretty typical of the other planets, with a small eccentricity of just 0.05. Now, this perhaps isn't so surprising. After all, if the eccentricity were higher than, say, 0.7, it would actually occasionally overlap with Mars's orbit and cause significant disruption to the inner planets. And yet, looking at Jupiter analogs detected via radial velocity, we see that half of them have eccentricities of 0.3 or higher, and only about a quarter of them have eccentricities consistent with that of our Jupiter. There really shouldn't be any strong detection bias towards eccentric planets either, so eccentric Jupiters genuinely appear surprisingly common. So put together, we have that 10% of Sun-like stars have a Jupiter-like planet in them, and of those only a quarter have an orbital shape consistent with that of Jupiter. Fold that in with the lack of any super-Earth in our system, and well, we seem to live in quite the house of curiosities. What these findings tell us is that a solar system like our own is indeed an unusual outcome. We are the 1%ers, at least if we agree that Jupiter is a valid proxy. This leaves an enormous number of unanswered questions still. How many of these have rocky Earth-sized planets? How many of those are at the right distance for liquid water? And how many of those have an atmosphere, plate tectonics, magnetic fields, and large moons? And are those criteria even necessary to constitute a solar system analog? These are big questions, and ones that we aren't able to fully answer yet. But we have to face the very real observational result that the solar system is, at a minimum, an unusual outcome of planet formation, and quite possibly an outrageously rare one. The mediocrity principle fails us here, but given the vast numbers of stars in our cosmos, solar system analogs surely do exist somewhere. But this really misses the point. Listen closely, and you can hear that the universe is trying to tell us something profound here. The way things are here, the configuration, architecture, and nature of our planetary system, they are not normal. You are not normal. None of us are. So here's to the weirdos, to the freaks of the universe that might ultimately represent the only way for the universe to know itself. So until next time, stay thoughtful and stay curious. Thank you so much for watching, everybody. This week, I just want to thank two of our long-time supporters, that is Methven Forbes and Tom Donkin, who are part of our inaugural Small Council event happening this week. Thank you so much for your support. If you too want to help out our research group, the Cool Worlds Lab, then be sure to click the link up above. And until next time, have an awesome day out there.